Okay, this is problem 3 of the AP Physics 1 force packet. What we have is we have a hanging sign hanging by these two angled ropes here, and nothing's moving in the problem. And so when nothing's moving, this is a static equilibrium problem. Static equilibrium. And all that means is the object's not moving, and that means that the forces are going to balance. So all the forces on this particular sign are going to balance out. I'm going to start off by doing what I always do, which is draw a force diagram for the object, a free body diagram as they're called. And so I've got my 20 kilogram sign right here, and it's got three forces on it. It's got this main force of gravity, which we know is equal to mass times gravity, and we can go ahead and label it as 200 newtons. And remember, the negative 200 newtons means it would point down. It would be a downward pointing force, but we might use the magnitude of it when we're actually solving. And we've got two ropes. Sorry, we have this rope and we have this rope. And these ropes are at angles. This one is a 40-degree angle, and they're telling me that this one is a 60-degree angle. Anytime we have angled forces, what we're going to want to do is we're going to want to make components for each of these forces, because we don't want to add and subtract angled forces. We can't do that. We have to have all our forces pointed either horizontally or vertically, so we can find the net force horizontally and we can find the net force vertically. In this case, since all the forces balance, we know that the net force, both horizontally and vertically, is going to be 0. And so that's what we're going to do next. We're going to make components for these angled forces. You can do your components two ways. You can draw them up and over, or you can start here and you can draw them over and up. And I'm going to draw them over and up just so they don't get in each other's way. So let's start with this one over here, the one on the right. This force is pointed up and to the right. So you have to have a component that's up and a component that's to the right. And I'm going to draw it as a right triangle. So that would be my component that's pointed to the right. This would be my component that's up, and it would make a right triangle like that. Similarly, I would do one for the left. This force is pointed up and to the left, and so I would have components pointed up and to the left, like there. And then you can tell that those are going to be right triangles. And remember, once I have the two components, then I don't need to worry about the angled force the rest of the problem. I can focus on just the two components, and I can do my net force that way. Once you've got this, you're going to want to label these because these are two different ropes with two different tensions. And so we want to label them. I'm going to call this one T1 and this one T2. And then I'm going to find amounts for each of the forces. This 40 degrees from geometry is going to end up right here. And this 60 degrees is going to end up right here. And then we can use sine and cosine to figure out the magnitude of the components. So this one looks like it's going to be T1 times the sine of 40 degrees. And this one looks like it's going to be the T1 times the cosine of 40 degrees. So this one is the vertical component. This one is the horizontal component. And if you're not sure where those came from, we're just using sine and cosine, right? Sine of theta equals opposite over hypotenuse. And you've got cosine of theta equals adjacent over hypotenuse. We're going to do the same thing on the left. And so this is going to be T2 this time, times the sine of 60 degrees. And this one will be T2 times the cosine of 60 degrees. And now that we've labeled the magnitude of each of our components, we don't need to worry about the angled forces anymore. This T1, these T2, the overall angled force, we can ignore them the rest of the problem. We have the components, we're going to work with the components. Next thing we're going to do is we're going to apply Newton's second law. So the net force is 0, so that means in the horizontal direction all the forces must balance out, and in the vertical direction all the forces must balance out. We're going to start with the horizontal. We have two forces. We have this T1 cosine 40 here pulling this object to the right, and we have the T2 cosine 60 pulling it back to the left. And so since these two are going to balance, I'm going to write an equation that shows that. I have T1 times the cosine of 40 is equal to T2 times the cosine of 60. All I'm doing is saying that this horizontal force is the same size or magnitude as this horizontal force. And that's what I'm saying. They have the same magnitude. They're equal to each other. I'm going to do the same thing with the vertical forces. I have 3 vertical forces. I have T1 sine of 40 pointed up. I have a T2 sine of 60 pointed up. And I have a gravity pointed down. And so when I add these 2 upward forces together, they should cancel out gravity, which is pointed down. And so I'm going to use only the magnitudes in this, so I make sure that I don't mess up a negative somewhere in there. And so I'm going to have T1 sine of 40 plus T2 sine of 60. Those are my 2 upward forces, and they're going to equal 200. Those are going to be my magnitude of my gravity force. And these are the main 2 formulas that I'm going to be working with the rest of the problem. This is Newton's second law in the horizontal and the vertical direction. And in both cases, the net force was 0. That's all we did. We used net force to find both of them, horizontal and vertical. At this point, I have a situation where I have 2 equations and the same 2 unknowns in both equations. I don't know what T1 is. I don't know what T2 is. Same thing down here. These sines, cosines, they all are just decimals. I can actually replace them right now with actual decimals, and that might be easier to do, so we're not too worried about it. So I'm going to punch cosine, make sure my calculator's in degree mode. I'm going to punch cosine of 40 into the calculator, and I get 0.766, so times T1 equals, I'm going to punch cosine of 60 into the calculator, and I'm going to get 0.5. So 0.5 times T2. Just put some parentheses there to keep myself organized. And so all I did is take this first equation and replace the cosines with decimals. Then I'm going to do the same thing for this equation. I'm going to put sine of 40 in the calculator. And so we got 0.643 times T1 plus, I'm going to put sine of 60 into the calculator, 0.866 times T2, and that's going to equal 200. And so I just want to emphasize that the sine and cosine of angles, they're just decimals. You can treat them just like decimals, and now we've basically replaced them with decimals down here. So what we have to do is we have to rearrange one of these formulas and plug it into the other one. We're going to substitute so we can eliminate one of the variables. We don't know 2 of the variables, we don't know T1 or T2, so we're going to have to rearrange one of these. This top one is the easiest one, for T1 or T2, and then substitute it down in here so we can solve. And so I'm going to scoot this up here. I'm going to solve for T1 in this first one. And so I'm going to take this and I'm going to rearrange it for T1. And so T1 is going to be equal to 0.5 T2 divided by 0.766. All I did was divide the 0.766 to the other side. And when I do that in the calculator, I get 0.653 times T2. So this is how T1 and T2 are related. T1 is equal to 0.653 times T2. And what I can do now is I can take that and I can substitute it into my second formula. I guess my second formula is right here, the decimal version. And so I'm going to go ahead and do that now. I'm going to say 0.643, but instead of T1, I'm going to substitute this in for T1, because remember this is equal to T1. So we've got 0.653 times T2 plus 0.866 times T2 equals 200. And at this point, we can go ahead and multiply these out. So 0.643 times 0.653 gives me 0.419 times T2 plus 0.866 times T2 equals 200. Scoot this up a little bit. These are like terms. They have the same variable in them. We can add them together. We can combine them. We can add the 0.419 and the 0.866 together. And I end up with 1.285 times T2 equals 200. I'm sorry, 200. Try to do a T1 there. And now I can solve for T2 just by dividing. So 200 divided by 1.285, and I get T2 is equal to 155.6 newtons. And if you don't get this exactly, it's because you're probably rounding a little bit different than me, but you should get something in the 155 region. And so now that I have T2, it's a piece of cake to go back and find T1. I just have to substitute it back in to my original formula here. And so I'll go ahead and I'll say T1, I guess I'll use the decimal version. So 0.766 times T1 equals 0.5, but now I know what T2 is. It's 155.6. And then I can go ahead and solve this for T1. So punch it into the calculator. Hopefully you don't need a step-by-step on how to do this. And I end up with T1 equals 101.6 newtons. And I did it. I solved for the tension in both of the ropes. This situation is really important. This situation where we have two variables and two equations with the same two variables in them, we need to remember how to do this. We need to be able to rearrange one and substitute it into the other in order to eliminate one of the variables and solve for it. And the other thing we need to keep in mind is any time that we see static equilibrium, or something's not moving, or even something's moving at constant speed, as long as the acceleration is 0, then our forces must balance, and we have to proceed accordingly. But other than that, it's the same situation every time. Draw a force diagram, analyze the forces, apply the net force, and go from there.